Hello and welcome to the Forward Together podcast. My guest today is Dr. Nick Solomey, professor of physics at Wichita State. Dr. Solomey is doing some great and fascinating work with NASA through his research on neutrinos. Welcome to the Forward Together podcast, Dr. Solomey. Well, it's good to have you here with me today on the Forward Together podcast to talk about all things physics. And we have the expert here, or one of the experts here, I should say, on physics, longtime physics professor here at Wichita State. And so I wanted to ask you some questions, really trying to get people to understand some of the relevant things that you're working on, others in your department are working on, that relate to things that they might be thinking, how does this apply to me in my world? But before we get into the nitty gritty, in your work with NASA, you've been building a neutrino detector. Neutrinos is what you're detecting, because you had to tell me this at one point what a neutrino was. And so can you explain what that means and why it's important to the everyday individual?
Well, the neutrino is a subatomic particle, one of the most mysterious. And it doesn't obey what's like the standard model of particle physics. It has a long history, but normally when people say you're building a neutrino detector, the first thing that should come to mind is something supermassive, larger than this building, and very deep underground, because that's what they all look like. But in 2016, we had this speaker who came from the University of Virginia, and he made a silly statement, and I was not so polite, so I interrogated him. His silly statement was we would soon be at the level where the solar neutrinos will dominate the background search for dark matter. And I said, well, that's not, his idea was you can never get around this problem. My idea was that, look, Voyager space probe is now 165 astronomical units away from Earth. It's 6 orders of magnitude less solar neutrinos out there. So clearly you could resolve that problem. The next day when I woke up, I said, what happens when you take a neutrino detector or any detector close to the sun? And I did a calculation, and it turns out that you could get 46,000 times more neutrinos if you're just where NASA's able to go close to the sun. And that's a huge increase. What that means is a 1 kilogram detector here on Earth would act like a 46,000 kilogram detector when you put it that close to the sun. And at that time in 2016, when I was thinking of this idea, I knew that NASA was about to launch the Solar Probe Plus, which is going to go close to the sun every 90 days, which, by the way, it launched in 2018. It's been doing ever since, working great. And so I said to NASA, we have an opportunity to do something really unique here. This isn't the first time particle physics has gotten involved with NASA. Back in the 1990s, a group of scientists said, let's take a gamma ray telescope and let's put it above the atmosphere of the Earth, and we could look for gamma rays in the sky. And they did that. They launched it in 1992, and they saw for the very first time gamma rays coming from objects they didn't even know existed. Because high energy gamma rays don't make it to the surface of the Earth. So NASA was able to put this above and there's a similar idea here. We could take a very small neutrino detector, we could put it someplace where NASA could deliver it, and really close to the sun, and it could act like a supermassive detector here on Earth. But it's yet very small, and it's very affordable. Well, affordable in the sense that the detector I'm envisioning for our first spacecraft close to the sun is only going to be about 120 kilograms of active volume. And
So how big is that?
so that'll be like 46,000 times bigger.
I know, but the actual...
The actual volume, about 0.7 meters, 2.5 feet, with about a foot in diameter.
Okay, so not too big.
No, it's heavy material, so it's not too big.
So tell us why we need to detect neutrinos. And what are
Right.
You said there's a
It's a subatomic particle that's very fundamental. It has a lot of mysteries in the sense that it could go through matter as if matter is not there. It weakly interacts. The standard model of particle physics says it should be massless, but we've just proven that it has mass at about, about 5 10 years ago. And this is exciting because now we need to understand how what the mechanism is doing this and what implication it has on other elementary particles. The Higgs field is supposed to give all particles their mass, but that doesn't seem to be the case with the neutrino. It's getting its mass in a completely different mechanism than the Higgs field. And so this isn't part of the standard model. And I've been in particle physics since I was 17 years old. That's when I first went to Argonne National Lab as a summer intern, worked then at Fermilab a little bit. I make it to CERN just before I turned 21. I spent 8 years at CERN on my PhD thesis and did a lot of great work with them. I came back from CERN and worked on a very famous experiment that has my most famous result in physics. But in about year 2000, I started going into neutrino physics with the Fermilab High Energy Neutrino Program. And we have a great group of scientists here that work on neutrino physics, currently led by Professor Matt Muther, with Holger Meyer and myself as aiding him. And he's been working on this NOVA experiment with us and the future DUNE experiment. These are very massive, several billion-dollar projects, deep underground, but they'll be looking at higher energy neutrinos directly from an accelerator. Whereas what I want to do with the inside of the sun is to study the solar neutrinos. So solar neutrinos are very low energy. They're harder to detect because they're lower energy, but they could help NASA do things that nothing else can. If we could get close enough to the sun and collect a large amount of data, it doesn't have to be super large like we have here on Earth, but every event we collect is equivalent to 900 events you collect here on Earth. And so if we collect just 100, we would be, fantastic for looking at not just the fusion core of the sun's size, but the inner core. So these layers in the sun are what's called fusion burning shells. They're not the entire core. They're just a thin layer where all the fusion of the sun is occurring. And one of the main stated goals of NASA is to understand how the sun works better. And this is why NASA is interested in the project. I'm interested in it for that reason also, but I'm also interested in it because I could do some unique particle physics that no one else could do. And that makes it exciting.
Okay. Well, you said earlier that they can go through mass, right?
They can go through matter, unhindered almost.
So through our bodies. And the average person who doesn't understand physics, and what does that actually mean, and why would that be something that you would point out?
Well, the neutrinos from the sun, if you look at your thumb, there's about 1,000 per second going through your thumb. That's just your thumb. The rest of your body is taking just as much a dose. And they're just so weakly interacting that they don't interact with anything. In fact, if you had a beam of neutrinos and you shot it through a light year of lead, half of them would still get out the other side. So that tells you how transparent they are to almost everything. And transparency shouldn't shock people. We have glass windows in our car and our houses, and light gets through it. So transparency, we know, does work for certain particles. At the same time, of course, there's like bricks where they're not transparent. But neutrinos seem to be transparent to all forms of matter. Well, maybe not dark matter. We haven't proven that one yet. But it seems to be, no matter what you make, no matter what density of matter you make it out of, neutrinos just go right through it like it's transparent, like photons go through a glass window.
So the bottom line in terms of the experiments that you're doing with NASA is really to understand more about how the sun works.
Yeah, NASA is interested in using this to understand how the sun works. There's another aspect that the astrophysics division in NASA is interested in, and that is if we could measure the actual shell, the fusion shell that the neutrinos are coming from, the inner radius as well as the outer radius, then we could see, is there dark matter trapped in the sun below and that's displacing the shells outwards? And that we could answer that question. So and dark matter and answering some of the properties of dark matter is like the second most important question in NASA's science goals. Yeah. And so that could be really exciting too.
So I know that your department as a whole has received quite a few grants over the last several years. And besides this research on neutrinos, can you give us just a quick rundown of some of the other research that's going on in the department?
Yeah, physics. We have, of course, my NASA work, which has been $3.8 million since its project started. But we also have the high energy physics neutrino projects, NOVA and DUNE, that's been receiving a good bit of funding over the last 5 years. We have a solid state physics research group that's been getting lots of students funded through their material science studies that they're doing. Some of them jointly with chemistry, some of them jointly with other physicists. And we have another scientist who's working on high performance computing, getting funding for that.
Okay. I mean, I know there's been a lot more activity since, I've been in central administration in the provost office. And and one of those things that has also happened over time is to have a PhD option for physics students, because we don't have a standalone PhD option for physics, but we do have applied math PhD and statistics PhD, and that can be utilized in this way.
I think this is a good plus. We have the Department of Mathematics, Statistics, and Physics. It's one department being run economically without huge amounts of costs for offices and overhead. But there's other departments around the United States that have made the joint departments of math and physics very successful to help each other grow. Caltech stands out the most. About 8 years before we merged physics with math, Caltech merged physics with math to make a department of physics, mathematics, and astronomy. And that has actually helped them grow their math research towards more applied towards physics, helped them grow their theoretical physics research with the aid of mathematicians, because a lot of mathematicians actually do very similar things to theorists. We have a recent hire in the Department of Mathematics, Statistics, and Physics, a Professor Dan Grady, who's actually a string theorist. And so he has the option to help us occasionally teach quantum mechanics. And his research is very much in line with our other theorist who's working on the Higgs boson, or our other theorists who are working on quantum mechanics. So I think it not only was a good economic merger, and I would hate to see the break it up, but at the same time, we have a physics track in the PhD program of applied mathematics, like we have a statistics track, like we have a mathematics track.
Yeah. So I'm glad to know that that's worked out well. And then back to Caltech, I mean, that's where JPL is. I mean, if they could do it, Wichita State can.
They're right outside the gate of JPL, and there's some great advantages to that. Don't forget that some of the first places that had a department that concentrated on space science were always located right next to a NASA lab. As you said, Caltech has the most famous space
Jet Propulsion Laboratory.
Yes, because they're right next to the Jet Propulsion Lab. But at the same time, there's University of Alabama right next to Marshall, and there's Rice University right next to Houston. And there's Florida University right next to Kennedy Space Center. So they've grown their space science and physics just because they're well located to cooperate with NASA.
No, I haven't. This isn't a part of this interview, really, but it's a little bit of a side. I grew up in Houston and lived down the street from the Johnson Space Center. Back in the day when I was a kid, you could just walk into the mission control and watch what was going on. That doesn't happen anymore.
I guess not.
Always had an interest in what's going on in space because of that experience. So you've been with Wichita State since 2007?
Yeah, that's right.
Time flies, right?
Time flies, yeah.
What makes our physics program special, and what do you tell prospective students and their families about physics to try to encourage those that have an interest in physics to come to Wichita State?
Well, we've had a lot of great successes with our physics students. They've gone off to some great future studies in the PhD programs elsewhere. They've gotten some very lucrative jobs. We have several students in the last few years that got their master's degree from me, and they're making, 3 times more than I'm making per year.
So make sure why you decided.
So, and that's very helpful that it's been successful in that way, that we could help educate the students to get really good jobs, and we place them in really good schools. At the same time, I have to ask the question always, would I have done this project here or somewhere else with NASA without having had the cooperation I've had from aerospace engineering? I've been working with aerospace engineering faculty ever since I started this NASA project, and it's really made us move the project ahead much faster. At the other schools have been at before I come here, I wouldn't have had that help. I would have had to go search at another university to get that kind of input. Here, it's just one building away.
Yeah.
And they're very cooperative, and they like working on it because it advances their students to do more aerospace engineering with our mission to the sun, which is demanding for some mission designs, and as well as our CubeSat mission that we hope to launch in June of 25.
Yeah. Well, and I think I'm glad you brought that up because, the size of the institution that we are, we're not a large, comprehensive research institution, but we are a research institution. And it's just much easier to get things done because of that in some ways. So I'm glad that you're having a good experience with the folks in aerospace engineering. So what are some emerging trends in physics, particularly the field of study? And go easy on us because, we're not physicists, most of us who are listening probably. Make sure you probably dumb it down a little bit. I hate to use that word, but make it a little bit more understandable for us, I guess.
Well, some of the most interesting things that are emerging in physics, because keep in mind, physics is not a new subject. Physics, you got Newton and Galileo who formulate some of the first postulates that we still teach our freshman students 400 years ago.
Yeah.
At the same time, we have, new quantum technology that's coming about, and we also have, in my realm of nuclear and particle physics, or astrophysics, or astroparticle physics, we have some very new ideas that are now beyond the standard model. The standard model of particle physics was formulated in 1960. By the way, that's before I was born. And that was just proven with the Higgs. But now we're seeing these violations of the standard model. And so that, why are these violations? And they all seem to be concentrated around the neutrino.
When you say violations, what do you mean?
Well, I mean, the neutrino, it's supposed to have no mass, and yet we now prove that it has a mass, and it's supposed to not be changing. So we now see it changing as it oscillates. Of course, these are related in the sense that the mass the neutrinos have is why it's oscillating between flavors as it flies away from your accelerator or flies away from the sun as you study at different distances. And so these are not explainable in what's called the standard model of particle physics. And that's what we want to have an explanation of. That seems
so
to
that's
be
when you
eluding
say
us.
violation. It's
Yes.
not what we currently understand in terms of what we know about physics. It's something new.
Right.
Right. But you call it a violation.
Yeah. I call it a violation.
Okay.
Because I was taught the standard model of particle physics was supposed to be the answer.
Yeah. Okay. Got it. All right. So just for fun, what science fiction movie or TV show do you feel is most accurate in terms of physics?
Okay.
I know this is a tough one.
Well, this is a tough question, and the way I thought about answering this is everyone has seen movies like Star Trek, and they talk about faster than light travel by a lot, and they do it with a general relativity effect that's on paper theoretically possible. That if you want to go on a piece of paper between A and B, and if you're able to fold that piece of paper such that those 2 points A and B touch, they go through it. And that's general relativity. But there's another way to look at this, and that is that look at an atom or a molecule like water. You have hydrogen, oxygen. The electrons are being shared. That's how they're bond together. But yet the nucleus of an atom and the size that the electron has to travel is almost the same scale as a galaxy is to other galaxies. And yet it could do it as faster than light transportation. It does it through a quantum mechanics effect. And we have a very good professor, Professor Berman, who does a lot of quantum mechanics research here at Wichita State. And there's an example of how maybe quantum mechanics could explain some of these faster than light travels. So in some sense, these programs are kind of fun to watch. And some of there's whole shows on what's the physics behind these faster than light travels. And that makes it kind of fun to think about that processes because we're studying them. Some of them we're even studying here in the theoretical realm. Others are just whimsical hopes. But there is like the Big Bang Theory. It does try to relate some physics to the real life endeavors of scientists and their social life. And that's kind of fun to see as well. But I just think it's it's great that we could talk about how these different spacecrafts might be able to go from one place to another really quickly. I used an example of the curved warp space-time with a piece of paper like on Star Trek, but there's the quantum mechanics one where you just think of that size of the atom is mostly empty space. The nucleus is so far away from the electrons that they really can't even resolve each other, but they can feel the forces of each other, the electromagnetic forces of each other. But yet somehow or another, those electrons and hydrogen and oxygen go instantaneously one to the other. And of course, it's a wave effect and it's a quantum mechanics effect. But so those are kind of fun, and I find it fun and exciting because there's plausible explanations. Don't expect anyone to invent such a drive in the near future, but they're kind of fun to watch in that sense. And
I just love the Big Bang Theory show. It's not on
good.
anymore, but just the dynamics of the characters.
You can always enjoy the reruns.
Well, Nick, it's good to see you. Thank you for the work that you're doing and your department's doing. It matters to obviously what you've been telling us. It matters. This stuff matters
And
to
we've
our
been,
future.
We've been having a very good success with our students here at Wichita State, and the fact that they enjoy the studies with us and that they've been successful after they leave us either in a job or to other education. I think that's a plus, that we're doing it well for our region of Kansas that we're serving.
Yeah. Well, thank you so much. Good to see you.
And thank you all for listening. And be sure to rate, review, and subscribe wherever you listen to the Forward Together podcast. Go Shockers!
Sponsorship for the Forward Together podcast is provided by Scott Rice Office Works and the Shocker Store. Additional thanks to Nair Amp, WSU Carpentry Shop, and Go Create.